Hello, Mr. Kitchen, Cobleskill, Richmondville High School Physics. These are the notes that we do in class on conservation of work and energy. We're going to take a look at two things side by side. So I'm going to begin on the left here with problems where we only have internal forces. And if you recall, our internal forces are our GEMs, gravitational, electrical, mechanical, and spring problems. But most importantly, these have no friction involved or any kind of other external forces. When we're solving problems like that, we usually begin with conservation of total mechanical energy statement, TME before equals TME after. And at the next level, we can expand that out. Total mechanical energy is potential energy of a spring before, delta PE before, kinetic energy before. You add up all the types of energy that you have, and then we have potential energy of a spring after, gravitational potential after, delta PE, and kinetic energy after. Now what you see I've done in the notes is just to send a few of those to zero. What we're doing as we work our way through these problems is trying to identify terms that will go away. And at this level, we might say, well, we don't have any potential energy. So at this point, we'd be looking for things that are zeros. Now on the next level, we can expand things out. And now I'm looking really for variables that are going to cancel out. So let's say I wrote out this equation in terms of detail mg delta h and 1/2 mvb squared and so on, and I see that I have a mass term in, or a mass quantity in every single term, and I can cancel that out. And after that, I would just go ahead and substitute it in and solve the problem. So let me show you how this works. We're going to take a look at a problem. Jane looking for Tarzan. She's going to run at top speed, her top speed, 5.9 meters per second, grabs a vine hanging from a tall tree, and we want to figure out, well, how high does she swing? So she's starting out, we show in the little picture, with some kinetic energy, grabs onto the vine, and she's going to lose her kinetic energy and gain gravitational potential. Here we have no external forces, so the total mechanical energy before is equal to the total mechanical energy after. And when I start writing that out, I see that the gravitational potential energy before is zero, and the kinetic energy after is zero. So I don't have to worry about those terms. Then I write out the formulas in more detail. 1/2 mv before squared is equal to mg delta h after, and mass appears on both sides, so that also cancels out. After that, I just solve for the variable that I need, which is the change in height afterwards. That turns out to be vb squared over 2g. Substitute and solve. Now, over here, we're going to talk about what do we do if we have external forces. And external forces include friction or any other type of force that's adding or removing energy from the system. These forces are going to do positive work if they're increasing the total mechanical energy of a system, or going to do negative work if they decrease the total mechanical energy of a system. Friction usually does negative work, but for example, with positive work, you might have an elevator that's being lifted up in the air. The motor on the elevator is doing positive work on that elevator and adding mechanical energy. So the equation that we start out with is similar to what we had before. We got total mechanical energy before, but now we're either going to add or subtract, sometimes both, the work done by the external force, and that's equal to the total mechanical energy after. Once again, we can work at various levels. The next thing that I can do is take total mechanical energy and put it in terms of symbols, and then I'd look for things that would zero out. My next level, I'm going to put it in terms of detail information, maybe look for variables that cancel out, and then solve. I didn't go through that whole thing just for lack of space. So we're going to take a look at an example here. We've got an inclined plane, a 22 kilogram block at the top of a 3.2 meter tall inclined plane. It slides down the inclined plane, and at the bottom it has a kinetic energy of 390 joules. So the question is, how much energy is lost? And when you see that term lost energy really isn't lost. It's going to go to the work that's done by friction. So I got total mechanical energy before, and that's why I've said a minus sign there, because we have friction, and that's going to subtract energy from the system. So minus the work done by the external force is equal to the total mechanical energy after. I write that out in terms of potential and kinetic energy symbols, and the kinetic energy before goes to zero. We don't have any kinetic energy at the top, and the potential energy goes to zero. We don't have any potential energy of gravity at the bottom. What I'm left with, I'm solving for the work done by the external force. So I've done a little bit of algebra there, bring the work done by the external over to the left-hand side. Then I bring in some symbols, mg delta hb. Now I've left the kinetic energy after as Ke sub A because I've been given that number, that's 390 joules. So we need to think ahead a little bit. I don't want to go into 1/2 mv squared. I don't know that information. Now the work done by the external force, and we can substitute in the numbers that we have for mg and delta H, subtract the 390 joules, and I end up with 3.0 E2 joules. We're giving our answer to 2 sig figs.